I'm Miss Dooley. I'm in room 802. Some of you have me, some of you have Miss Williamson, but we're going to do a quick little video homework tonight over phase changes. So we have time to do the homework in class with your teacher tomorrow. Isn't that a fantastic idea? So we're talking about phase changes. We talked about solids, liquids, and gases in class today. And now we need to talk about what happens when they go between phases. I would definitely take a few notes over the slides that you're going to see. I'm going to try to keep this short and sweet for you. So these are some different phase changes. What you'll notice is where you're looking at the solid, that's right about right here. When you look at the microscopic view, notice how organized and rigid and patterned they are. They have an arrangement, they stick to that arrangement. That's what makes them a solid. Very, very tight, compact. The molecules are actually vibrating ever so slightly. And so what happens is there's so much energy contained in those molecules that if you give it a little bit of heat, and that solid absorbs some heat, check out what happens. It's going to go on this line here, and it's going to melt, and it's going to turn into a liquid. You know that. But check out what happens to those molecules in the microscopic view. They've lost their arrangement. They're still close together. They bump into each other a little bit, but they are not organized anymore. If I add a little bit more heat to that liquid, well, of course, we make a gas. So we can make some water vapor if we're talking about water. Notice the pattern of the molecules now. Those little are trying to show you that those molecules are moving very, very quickly. They've got a lot of kinetic energy. They are literally bouncing off of the walls. If we could somehow tag all the gas molecules in the room right now, you'd be amazed at what was happening and how fast they move. And then the same is true when we go backwards. So when we go backwards, those gas molecules start to cool off. If you've ever walked outside in the morning and your grass has been wet, what happened overnight is when it's warm outside, all the moisture in the air evaporates and turns into water vapor, and that's what makes it feel humid outside. And so that humidity, as it cools down at night and the sun goes down, the water can condense. So the word is condensation, and it forms on the blades of grass in your yard. It doesn't happen every night. It depends on something that the weatherman calls the dew point. It also happens when you drink a soda. If you get a can of Coke and you leave it out on the table for too long, it starts to form condensation on the can. That is not any liquid coming out of the can. It's really the gas in the air cooling off and condensing on the side of your can. So it is cooling off the air around it, and the air is, or the water in the air is sticking to your can. And so now we've got condensation, and so that liquid will cool off even more, and it will freeze and turn back into a solid. In water's case, it turns into ice. And so these are typical phase changes that you've grown up understanding and knowing. We have freezing point, melting point, boiling point. And so all of these are going to apply to today's conversation. The ones that you may not be aware of are these guys right here. So if this solid skips the liquid phase and turns into a gas over here, it's a weird word called sublimation. There was a cool band in the 90s called Sublime. I loved those guys in college. He died. Don't do drugs. Just say no. And so if something undergoes sublimation, it totally skips the liquid phase. Some of you have seen something that does that. So here is my lovely artistic drawing of a block of dry ice. So dry ice will undergo sublimation. When you take dry ice out of his special freezer, his special cooler, because he can't live in a regular cooler, it's not cold enough, it gets so freaked out because it's like putting an ice cube on the sun. It is so hot in our environment for dry ice, it literally freaks out and it skips the liquid phase and it turns directly into a gas. So it's really, really cool and it's so fun to play with. Come back on Friday. We might have to show you some. Oh, wait. It will be Friday tomorrow. So we will play with some dry ice in class on Friday, so make sure you are here. All right, so this dry ice undergoes sublimation, turns directly into a gas. It's one of the unique substances that you'll see in your lifetime that does that. So the weirder thing is to watch it go from its gas phase and turn straight into a solid, skipping that liquid phase. So it's kind of like it's freezing, but it never turns into a liquid. So we have a word for that. It's called deposition. Deposition. And so deposition just means it's turning into a solid. Sometimes you're going to see that word called solidification, but deposition is the fancy word for a gas turning back into a solid. We can't show you that because we don't have a special dry ice cooler that can get cold enough, so we can show you how when the dry ice cools off, it will turn back into a solid. So what you haven't seen before is liquid carbon dioxide. So liquid carbon dioxide does not exist at room temperature and at room pressure, which we will talk about in a little bit. So those are phase changes. Hopefully you took a few notes over those guys and you're ready to go. Here's just another view of what we just looked at. So this is that weird zone here where the dry ice skips the liquid phase, but most of the substances you're familiar with will go from solid to liquid to gas, back to liquid, back to solid. So over here on the left, that's a special case. So this is just a different representation of what you just saw, but now we have some factors that come into play. So check out what we've got on our different axis. So here on the x-axis, we have heat energy. And over here on the y-axis, we have temperature. And so those are really important. A lot of people think that heat and temperature are the same thing, and they are not, okay? Heat is the amount of energy coming in or going out of a system in the form of heat. Temperature is the average kinetic energy of the particles. It's an average of all of the movement of the particles based on how hot or how cold they are. You should know by now, when things get warmer, they go faster. When things get colder, they slow down. And so that's a large part of what you're seeing with these molecules and all of these representations. And so here we go. Down here, we're at solid. So I would definitely draw maybe an X and a Y axis. I would label them with heat and temperature. You can abbreviate temperature as a capital T. We do it all the time. And so on this diagonal line here, what's actually happening is we are adding energy to the solid. Imagine that that solid was ice. So if this solid was ice, we're adding energy to the ice, to the ice, to the ice. Well, what's the ice going to do? Well, the temperature is going to go up because it's going up this hill. But when it gets to this point, it's going to start to melt, and it goes straight across instead of diagonal. Now, this is huge. We really want you to understand what's happening here. And so let me make it prettier. So on this flat line right here that we have, this right here represents melting when we're going this direction. When we're going the opposite direction, we'll talk about that in just a minute. So the solid warms up, going up the diagonal, and then it melts and it goes flat. So what does flat represent? We want you to understand this in a big bad way. Okay, so I maybe would point to that, and that is the phase change. Here is my abbreviation for change. It is a triangle. During a phase change, the temperature is constant. It will not increase. So go with me here. All right, if you've been to Chicken Express lately and you've ordered yourself a nice sweet tea, what you've got in front of you is a cup it's filled with tea, and it's filled with ice. Here's what I know. I know that the environment is warmer and the tea is cold. So what that means is that heat always travels from warm to cold. So the environment is warming up my tea, which is why we put it in a styrofoam cup. And so what's happening right now is that the environment is making that ice melt, and it is trying to warm up your tea. But let's think about what's really in there right now. Right now, we've got a liquid, and we have the ice that is a solid. When you've got two phases in the same container at the same time, that represents a phase change, and that temperature is constant. Here's what I know. If I stuck a thermometer down in that tea, it's going to be exactly 0 degrees Celsius, because that is the temperature where ice will melt and turn into water. So it will stay at 0 degrees Celsius until all of the ice is gone. Once all of the ice is gone, here we go back to our graph, and our liquid, there's no more ice, it's liquid now, and it will start to increase in temperature. Notice how the molecules are moving further apart and becoming less organized. So the liquid gets warmer and warmer and warmer going up the hill. It stops here, and then it will do the same thing. It goes across. Well, at this point, it's going between a liquid phase and a gas phase. So imagine the same cup of tea that you had a moment ago, but now that cup of tea has no more ice, and it's starting to evaporate and turn into gas. So you've got your gas escaping, and you've got your liquid in the cup. And so at this point, we call this the boiling point or the vaporization point, because it's turning into a vapor. So it's not just boils. You could also add the word evaporate underneath the word boils. But again, because I know that water boils or evaporates at 100 degrees. I know those molecules at the surface are warm enough to escape into the gas phase. And so then what's going to happen is once it totally has become a gas, it gives license for that gas to increase in temperature. Those molecules move further and further apart, and they've got tons and tons of kinetic energy, and they're literally bouncing off the walls. Now, we could do the same exact thing if we were going the opposite direction. We can do the same exact thing. It's just literally backwards. We start off with a lot of energy and high temperatures, and we cool off, cool off, cool off. We get to this point. Our gas starts to condense and turn into dew or liquid, and the temperature stays the same. Once it all turns back into a liquid, the liquid is allowed to get colder and colder and colder, and it hits here, and then that liquid starts to freeze, and the temperature stays the same until all the liquid is turned into a solid, and the solid starts to drop in temperature. So we call this on the way down a cooling curve. And when we were doing it a moment ago, we would have called that a warming curve as we were going up. So some key points to remember. During the phase change, the temperature remains constant, but on the diagonal, heat is added and the temperature changes. This is just a little bit prettier of a version of what we just looked at, but not a lot of new information there. Just labeled everything a little prettier for you. And our last graph is called a phase diagram. In a phase diagram, they're telling you all of the conditions that it must be necessary for a substance to exist in a certain phase. If I want water to be a liquid, I need to know his temperature down here on the X and his pressure over here on the Y. My former students effectively call this a butt diagram. Look at it closely, you'll start to see it. So we have several things I need you to note and look at here and maybe label. And so I would draw an X and Y axis again. Label temperature on the X, pressure, that's a new one we haven't talked about yet, on the Y axis. ATM is called atmospheres. The pressure in your room today is about 1 atmosphere. That is considered normal, standard, everyday pressure in a room is 1 atmosphere. And so that is important to note in just a moment. But here's what I would do on your map. So this is obviously the phase diagram for water, but we're not always going to give you a phase diagram for water. Every substance in the world has one of these, and it tells us what conditions does it take to make it ice? What conditions does it take to make it water? What conditions does it take to make it water vapor? And so it can tell me what variables to play with to get the phase I need. And so I would put a big S in this section. This is your solid section. Your water is your L, or your liquid section. And your water vapor, of course, is your gas section. So you can definitely see where all 3 phases exist in different conditions. So then I would also like to point out right here, maybe make a little mark on your paper right about here, and we're going to call that 1 atmosphere. There's the 1. I was like, I thought there was a 1 labeled. It is. It's behind my circle. So we're going to label that with 1 atmosphere. So put a little 1 somewhere on your graph, and then draw a line straight across and then down, and then down, wherever it hits those lines that you drew. And so this is really important. At 1 atmosphere, wherever it crosses the line here and here is a phase change. So X is marking our phase change, which is what we've been talking about today. And so from a solid to a liquid, obviously, that's melt. From liquid to gas, that is vapor. Or boiling or evaporation, any of those. Same thing is true if we go backwards. So water vapor back to water is condensation. I'm going to abbreviate that. And water back to ice, that is what we call freezing. So that's the freezing point. So the X, it's a little bit hard to see, apologize there. So the X here and the X here are marking the point at which the phase is going to change. And so we can go straight down from there and we can tell you what temperature that is. Water freezes at 0. Water vaporizes or boils at 100. And so whatever chemical we give you, the same rules apply, but the numbers at the bottom will be different. But you still start out at 1 atmosphere. The next thing we'll talk about is this point right here. This is called the triple point. This is why the kids call it a butt diagram. And so the triple point are the exact conditions. There's your pressure and your temperature that would be necessary to have a beaker and to have all 3 phases in that beaker at the same time, which would be so cool. What that means is that you would see water floating around in the beaker. You would see ice cubes floating on top, and you would see steam escaping all at the same time. It would be creepy, freaky, weird. Here's the problem. I can't show that to you because we've got almost freezing temperatures here, but this is the problem. I cannot get the pressure of a system almost to 0 and take the pressure out of this room to show you because we would all die. So I'm choosing not to do that demo today. So this is a phase diagram. The last point we need to talk about quickly, and we'll remediate the rest in class tomorrow, is the critical point up here. This is the point where it will not exist as a liquid anymore. So you can draw a line straight up from this point. Everything past that point will be a gas. So past 374 degrees down here on the x-axis, that is the maximum temperature that water can ever achieve and still be a liquid. Past that point, it will be a gas no matter what the pressure is over on the y-axis. So just a different way to look at solids, liquids, and gases. We're taking it definitely up a level from what you knew from elementary and middle school. We are going to practice this all day long. A couple more representations to show you. That's it for the notes. So here's another one. It's a little bit prettier if you want to label yours a little bit better. This is another version of a phase diagram. And this is kind of where we're headed throughout the year, is just talking about energy in general. So we're over here a lot talking about phase changes, potential energy because the temperature's not changing. Kinetic energy, of course, is when it's moving. Talking about the temperature change, the speed of the molecules on those diagonal sections. The phase changes, if you remember, were those flat sections. These are all physical changes. Nothing cool or interesting or new happened. We just changed it from water to water vapor or ice to water. Nothing thrilling. In the spring, we're going to get to all this really cool stuff, chemical changes, thermodynamics, bonding, and that's kind of where we're headed. So I just wanted to show you that slide. Have a great night. Thanks for watching. See you tomorrow.